So speech recognition has been around for a long time. People have been trying to do it for 50 years. And it was one of the first success areas for machine learning algorithms. So the EM algorithm for hidden Markov models had a huge effect on speech recognition. It became the method of choice in the 1970s, and it's been the method of choice ever since. And the hidden Markov models they used, the way they interfaced with the acoustic data was by having Gaussian mixture models. So each state of a hidden Markov model would decide how well it fitted the data by saying how likely was that data given the Gaussian mixture model associated with that state of the hidden Markov model. That's the standard technology. And what's happened in the last few years is that deep neural nets have been shown to do a better job at saying whether a state of a hidden Markov model fits the data. And they work in the other direction. They say, given the acoustic data, can we predict which state of which hidden Markov model is the best fit? And having made those predictions, you then use the standard technology to figure out what the most likely sentence is. So you model each phoneme by a little hidden Markov model that has a few states. Sometimes for a phoneme you have many different hidden Markov models depending on the neighboring phonemes. But initially we just used one hidden Markov model per phoneme, roughly. There's a standard way to preprocess a sound wave in speech recognition, which is to get things called Kepstrel coefficients. They're not the best way to preprocess for neural nets because they're designed to throw away a lot of the data so that dumb machine learning methods can cope. With a deep neural net, you'd rather see more of the data and decide what to do with it. But for now, we'll use the coefficients that are standardly used. And you train up your neural net by first taking your database of speech, using a standard speech recognizer to decide at each point in the speech what the phoneme being said is. So the standard speech recognizer knows what words are being uttered, but it has to decide where the phonemes are. And then you can use that as training data for a neural net that will then do a better job. So some early research in that area was done by George Dahl and Abdul Rahman Mohamed. And they used a net like this. They started off with Mel-Kepstrel coefficients here, but after a while they switched to filter bank coefficients, which are a less preprocessed form of speech and actually work better with deep neural nets. And they just tried very deep, very wide neural nets. So this was done pretty much when GPUs first started being used. And so they could train nets with, so there's 4 million weights there and 4 million there and 4 million there. So they could train these nets. And in fact, using 7 hidden layers worked best. So that's got of the order of 50 million connections in it. They're training it up on not much data. There's only about 3 hours of data in the TIMIT database. And so pre-training was important here. So what they did was they pre-trained a restricted Boltzmann machine to learn 2,000 features of the Mel-Kepstrel coefficients or the filter bank coefficients. And it's a little window that it's looking at. It's 15 frames with 40 things per frame. They then pre-trained another Boltzmann machine to learn features of these features and so on. They did this for quite a few layers, and they basically discovered the more the better. Then the last layer of weights are not pre-trained, so they're started off at small random values or 0. And here they have the states of 61 different hidden Markov models, and each hidden Markov model has 3 possible states. And so they're trying to say, which phone is it, and which part of which phone is it, which are the 3 states of the hidden Markov model. And the 3 states in these hidden Markov models say it's the first bit of the phone, the middle bit of the phone, and the last bit of the phone. And this is a very well-tried database. It's the sort of speech equivalent of MNIST. At the time they did this, the record for speaker-independent methods was 24.4% error, and that involved averaging many systems. They initially got down to 23%, and then later on they got down to just over 20%. And they subsequently discovered that you can do just about the same by using a more complex preprocessing method that Marco Aurelio Ranzata will probably talk about in his tutorial later on in the summer school. I won't talk about that now. So speech recognition people saw this. That corresponds to like 10 years progress in speech recognition. And it happened sort of overnight with GPUs and neural nets. And they began to get excited. And so they tried it on more complicated problems. In fact, what happened was the students who did this went off to big speech labs and they took the code with them and they tried the same methods, almost identical code, on much more challenging speech recognition problems. And that turned into the Microsoft speech recognizer and some other speech recognizers. So the people who developed this took it to Microsoft, and Navdeep Jaitley, another student, took it to Google. Microsoft has already deployed a speech recognizer based on this because it works better than their previous one. Google's been developing the technology and now has it working quite a lot better than the thing that Navdeep Jaitley ported there. But it's essentially the same method. And if you look at how well these methods perform, you can compare them with the standard method, which is to use hidden Markov models with Gaussian mixture models. And we're not replacing the hidden Markov models, we're keeping those for now. We're just replacing the Gaussian mixture models with feedforward neural networks to say how well a state of a hidden Markov model fits the acoustic data. And this is done by 3 of the biggest speech groups. There's about half a dozen big speech groups, and these are 3 of the major ones. This was done at Microsoft. On TIMIT, they were training on 3 hours of data. Now they're training on 300 hours of data. And we call these things, it's complicated to know what to call them. We used to call them deep belief nets, but that's just how you initialize them, and then you train them with backpropagation as a neural net. So they're best called deep neural nets that are pre-trained as deep belief nets, but that's rather a mouthful. So the deep neural net gets 18.5% error instead of 27.4% error. That's a big improvement. And on a different test set for the same training set, it makes another big improvement. This is probably the most impressive result there, even though it doesn't look like it. This is done at IBM, who has probably the best speech recognizer for this task, which is a very well-studied task because it was used in DARPA competitions. And the IBM speech group managed to get from 18.8% error down to 17.5% error, and this was a very highly tuned system. So this system, many years of tuning have gone into it, and fairly quickly the deep neural nets beat it. At Microsoft, they tried it on voice search, and they got a big improvement, and they're now deploying it. At Google, they tried it on voice search. Microsoft says like 300 hours is a lot. Google thinks a lot is 5,000 hours. They got down to 12.3%, and I need another slide to show you where they started. They started with a lot more than 5,000 hours of training with the Gaussian mixture models, and they were getting 16% error. And so that's a huge improvement. They got rid of like a quarter of their errors. And it's even better now. They also did it on YouTube, which is a very hard task because it's all sorts of different speakers, and it's very poor quality. And although they didn't get such an impressive improvement, they did get a significant improvement on YouTube as well. So there's a paper coming out in Signal Processing magazine in the fall that has these results. Probably the most impressive thing about the paper is it has authors from the University of Toronto and MSR and IBM and Google, and getting these guys to be authors on the same paper is quite an achievement. And it basically is the consensus opinion that these guys are better than those guys. And so that's a big victory for these deep neural nets. Now on to the next application. We would like to get similar improvements in object recognition. A lot of work has been done on object recognition using neural nets. About half of it's been done by Jan and his students. And they, over the years, have developed better and better methods. And basically, we're piggybacking on the methods they've developed. So you use convolutional nets for the early features. You use rectified linear units. You use competitive interactions so that the strong features suppress the weak ones. And you use pooling. And you even use overlapping pooling. we have a critic called Jitendra Malik who thinks that the deep neural networks haven't really proved themselves for computer vision yet because they haven't been tried on severe enough tests. So I checked with Jitendra Malik and got him to say that if we could do the ImageNet task with 1,000 classes, then he would be impressed. And that was a good test of whether these deep neural networks really did work for object recognition. So the ImageNet database has millions of images trawled from the net. And there was a competition in 2010 where they took 1.3 million of these images, and they're high-resolution images, from 1,000 different classes. And the task is to train on these images and then be able to predict on new test images which of these 1,000 classes it is. Now, there's many reasons why this is hard, not just that there's 1,000 classes in the high-resolution images, but it's a bit arbitrary what the label is. So each image has one label, and the image might contain a fridge and a microwave and a sink, and the label would be dishwasher, because it's just in the corner of the image is a bit of a dishwasher. So it's tough to get the label right. There's many cases where you wouldn't get the label right, because the microwave's sitting right in the middle of the image, but it's not a microwave. So the neural net really has to hedge its bets. It has to sort of, in the higher layers, it has to have sort of guesses about all the various things it might be, so that it can guess the right thing, but also make other plausible guesses. And to evaluate these nets, you have to say, not just how well do they do at getting at their first choice, but do they get the right answer in their top 5 choices? Because that's a more reasonable way to deal with the fact that there's severe label noise here. It's a bit arbitrary what the thing's called. The winner of the 2010 competition got 47% error in their top choice and 25% error in the top 5 choices. Since then, there's been another competition where the test set isn't public. The people who won the next competition went back to this competition and showed their new method gets 45% error on this competition for the first choice. So that's the state of the art for this data, these 1.3 million training images for 1,000 classes. And we know that if we can beat that state of the art, Jitendra Malik will be impressed, which is important. So we essentially, Alex Krzyzewski developed his own version of Yann LeCun's kind of deep neural net, which has a number of extra tweaks to it. All the layers use rectified linear units. He trains, he first downsamples the images to 256 by 256 by doing some cropping, and a bit of downsampling, I think. And he then uses quite big patches, but not all is in the same location. That's a way of telling the neural net much more information about translation invariance. Because the objects in these nets are quite big, a patch that contains most of the image probably has the object in it. And when he trains, he actually shows it a bunch of different patches. At test time, he shows it 10 different patches, the 4 corners, the middle, and the horizontal reflections of all those. And all of them get to classify what's in the image, and then he takes a consensus. And that makes it work considerably better. And as a result of all this, he gets about state of the art. So his convolutional net is getting about, he keeps improving it, and I'm not sure he's measured the performance without our magic trick yet, but without our magic trick, it gets about 45% errors. But we now have a magic trick, which is a much better regularizer for the top layers of the net. So in the lower layers, it's convolutional, and I have a faint suspicion Jan may have explained convolutional nets. And in the higher layers, it's globally connected, and so there's many more parameters in these high layers. The good thing about convolutional is there aren't many free parameters. And so if it's going to overfit, it's going to overfit because of this global connectivity in the highest layers. And we use our magic new regularizer, which I'll explain in the next lecture. And that takes a net that's getting mid-40s error and gets it down to 39% error. And 19% instead of 25% for the top 5 choices. So this is significantly better than the previous state of the art. This is sort of comparable with the improvement we were getting in speech. And it comes from using standard deep neural net technology, plus an extra trick, and using GPUs, and using Alex Krzyzewski, who's very good at tuning things. Here's some examples from a slightly earlier version of his system. This system was not doing quite as well, but I happen to have the examples that shows the sort of things it can do. So that would be an ImageNet image, and the right answer is quail. You'll notice the beak's missing. These are the answers the net gave. These are the probabilities it associates with various answers. So it got quail second, so it's in the top 5, but it didn't get it first. The first answer it gives is otter, and since sort of I believe in this net, I'll make apologies for that. Otter's not a bad answer, because look at all this wet fur here. That looks just like the wet fur of an otter. And anyway, there's no beak. But notice the other 3 are all kinds of bird, and I'll bet you don't know whether that's a quail or a ruffed grouse or a partridge. This one I like. This is snowplow. This is a Canadian example. And it's very confident it's snowplow. But if you look at its other bets, it says drilling platform, garbage truck, and lifeboat, which are all quite plausible. In particular, lifeboat. Look at this again. Here's the flag at the front of the boat. Here's the bridge of the boat. Here's the flag at the back. Here's the surf. It's actually, lifeboat's a pretty plausible interpretation. You can see details well enough to know that's not a lifeboat. But if you blur your eyes a bit, that's a pretty good lifeboat. This is an example where it gets it completely wrong. The answer is scabbard. It thinks earthworm. We'll come back to that. Guillotine is a pretty good thing. You know, 2 big vertical things, that's a guillotine. This is contextual recognition. This is clearly jungle, and this is orange, so it's an orangutan. Broom is not bad as a big vertical thing. But why does it get earthworm first? Well, if you look carefully, you'll see the earthworms here. There's one earthworm, and there's the other earthworm. They're crawling across it from the grass. And there's many examples like that where you can see why it gets it wrong. I'll show you another one in a minute. Just to sort of emphasize how hard ImageNet is, here's some other examples. You see, I would have said microwave there. The right answer is dishwasher, and I can't even, I think there's a bit of dishwasher here. There's a bit of sink there. Sorry, the right answer is electric range, and there's a little bit of electric range here. So that's an example where it's obvious the net has to see all the main things in the image and then guess them. Here's an example of something that's fairly distributed. It's not like it's a single local convex object. It's occupying a large fraction of the image, and it gets it. And prison's not a bad bet for that kind of setup. It gets pictures as well as real things. These are from catalogs, and quite a lot of the things in ImageNet are like that. And here's my favorite example. This is some iPod headphones or something. It says corkscrew. Well, that's not so good. And lipstick, that's not so good. And screw, that's not so good. And then it says ant. And you think, ant? What? Why on earth does it think this is an ant? And then look at it. This is a great big ant that's just about to eat you. Here's its eyes, and here's its antennae. And that's the sort of green fly's blue. If you're a green fly, you don't want to see that. And I'm pretty convinced that's why it thinks it's an ant. You can see the ant there. Now, Alex does have some cases where he's back-propagated from the object class to ask which pixels in the image are most responsible for giving this answer. In other words, you find pixels where, when you change their intensities, your probability of the right answer changes a lot. And he can show for some images, like an image of a mite on a leaf, that the net is saying it's a mite because of the legs of the mite, which occupy a tiny fraction of the image. So we know in some cases that it really is getting the right answer for the right reasons. Obviously, we'd like to get something where we can look inside the net afterwards and say, yes, it said that was an ant because it thought that was an eye, and that was an eye, and that was an antenna. And in the lecture I give tomorrow, I'll talk about a system that has more chance of doing that. It doesn't do it yet, but it has a chance of actually, there's a chance you can look inside after it's learned and understand why it recognizes things. Here's another nice example of this is a barber chair, which it gets right. But cello's a bet, and you can see there's a sort of big diagonal bit here with some stuff going on. And that's sort of cello-like. Okay, that's it for object recognition. My prediction is over the next few years, as GPUs get faster and we get better at tuning up these big neural nets, those vision people will get quieter and quieter about how neural nets are no good. So I'm now going to talk a bit about retrieval. I started off working with Russ Salakudinov on document retrieval, and we came up with a way of doing extremely fast retrieval with not very high quality, but really, really fast, where what you do is you take a document represented as a bag of words, you use a very deep autoencoder to convert the document into a code of about 30 bits, so a very small binary code. And then you treat that neural net that converts bags of words into small binary codes as a hash function. That is, what you're going to do is take a document, the neural net will tell you where to put it in memory, and you'll have a pointer there back to the document, and from nearby memory locations you'll have pointers back to other documents, which are documents that have very similar codes. So if you want to find a document similar to this one, you don't have to do any search at all. You can have 1 billion documents. You go to the memory location associated with this document by the neural net, and then you start flipping bits of the address. And if you flip one bit of an address, you'll get the neighboring location. And then you look if that points to another document. So in effect, you can search a big database without really doing any search at all. Just a few machine instructions, you can start enumerating documents, a few machine instructions per document. Now, they won't be very high quality, so really you just use that for getting a shortlist. I call this supermarket search, because in a supermarket, well, yeah, when I first came to the States, I wanted to find anchovies. And so I asked where the sardines were, and so I went to the sardines, and then in supermarket search, you look around and there's the anchovies. Because supermarkets got this 2D shelf space that wraps around, and it puts similar things near one another. The problem is in North America, anchovies are with the pizza toppings, they're not next to the sardines. But that's just bad luck. If they had 32-dimensional supermarkets, they'd be much better off. In a 32-dimensional supermarket, you could have them next to the pizza toppings and next to the sardines. In fact, in a 32-dimensional supermarket, you could have the kosher things next to the non-kosher things, and you'd have the expensive things next to the cheap things, and you'd have the things that were expensive but are now very cheap because they're slightly off next to those. And with 32 dimensions, you can do amazing things in capturing similarity structure that you can't do in the 2 dimensions of a supermarket. And that's what's happening here. But the point is, normally with hashing, when you hash code something to a memory address, you can't use that to find similar things. You can use it to find if the identical thing is there, because it'll have the same address. But most hashing functions don't hash similar things to nearby addresses. But a neural net can do that. So the idea is spend a long time doing machine learning to get this really cool hashing function that allows you to match similar things, and then you can do searches really fast. So we've applied that to images. Let me say one more view of this. If you take a conventional computer, well, if you take retrieval, here's how retrieval, this is a slightly exaggerated claim. All retrieval works like this. You find some lists and then you intersect them. Well, if you're going to do that on a computer, you better find lists that can intersect fast. And there's one kind of list intersection a computer can do in one machine instruction, which is take 32 lists, each of which has about 500 million items, and intersect those 32 lists to find the one item that's in all those lists. And the way the lists work is, each bit of the memory address is a list, and if the bit's on, it's picking out 1/2 of the memory space. That's 500 million. And if the bit's off, it's picking out the other half of the memory space. So it's a list of all the addresses in that half of the memory space. And what the address bus does is intersect those 32 lists to give you the right address. And it does it in one machine instruction. That's the nice thing. And so another way of thinking about semantic hashing is, if you're going to intersect lists, do it the way the computer wants to do it. And so now all you have to do is take your task and map it onto that kind of list intersection. And that's what semantic hashing is doing. Okay. So for image retrieval, what we'd like to do is, instead of using captions, we'd like to, well, what we'd really like to do, of course, is extract objects from images, which is rather hard, and then use the objects in the images like you use the words in a document. A word in a document is quite good at retrieving similar documents because it has a lot of meaning associated with it. Whereas a pixel in an image has very little meaning associated with it. I mean, it might be red, it tells you something, but not much. And you'd like to get to objects. But if you can't do that, at least you'd like a neural net to get things that are better than individual pixels. And so we're going to try using semantic hashing for image retrieval. So we take images, we use a deep autoencoder to convert the image into a very short binary code from which you can very approximately reconstruct the image. And we're going to actually use a two-stage method. We'll use a neural net that gets a very short code, and using that very short code you can very quickly get a short list of, say, 100,000 images that are similar, or maybe 10,000 images that are probably similar. And then in that short list you can do a more accurate match using, say, a 256-bit binary code. Because even with 256 bits, that's only 4 words of memory, so you can afford to associate that with every image. And you can do a linear search through, say, 10,000 things, because comparing two 256-bit vectors to see how different they are can be done with machine instructions that operate on whole words and do XORs, so it can be done very fast. So a linear search through tens of thousands of things is extremely fast with these binary codes. So the question is, will our 256-bit binary codes work well enough to produce reasonable answers? So Alex designed an autoencoder like this. There are no principles whatsoever except that on a GPU, powers of 2 is a good idea, and he wanted to end up with 256, so he just kept doubling it until he got back to that. He inputs 32 by 32 color images. So these are small color images. You can still see a lot in an image like that. And what he's going to try and do is come up with codes for these images that allow him to find similar images. He's going to work on the CFAR10 database, which has labeled images to test the thing, but for training it, there's a huge number of unlabeled images that he can use for training. So if you go down to 256 bits and then find other images that have similar bit vectors, there's a test image, it wasn't used for training. Here's the closest other image, and this shows you the distances of these other images in bits. And so even 60 bits away is remarkably similar, since a sort of random one will be 128 bits away. At least it would if the bits were on and off equally often. And you can see here that most of the things retrieved have a kind of collar and tie, and they're all heads of people. This is what happens if you do Euclidean distance in pixel space. Obviously on a big database that will get you good things too. Notice though they don't have so many collars and ties. And another thing to notice is that many of the things that are closest in Euclidean distance also show up here. Like this woman here, right? She shows up in the 256-bit binary codes. She's also close in Euclidean distance. But this method is hundreds of times faster than doing Euclidean distance on the images. So it is a bit better than Euclidean distance, but another way of thinking about it is it does Euclidean distance extremely fast and gets similar performance. That works for a number of different kinds of scene. So here's kind of outdoor scenes. Again, Euclidean distance returns many of the same things as are found by the 256-bit binary codes, including things that are quite wrong. Like if you look carefully at this, you'll see that's like a water tank. It's nothing like these other things, but Euclidean distance gets it here, and the 256-bit codes get it there, which show that this thing has a very limited understanding of what's going on in images. It's fairly superficial similarity it's using. But again, think of this as a very fast way of getting things with very similar, which are very close in Euclidean distance. Here's an example where it definitely does better than Euclidean distance. So this is a little group of people. And if you look in the things that are returned by the 256-bit codes, there's 1, 2, 3, 4, 5, 6, maybe 7 groups of people. Whereas Euclidean distance alone gets 1 group of people, maybe, yeah. It's not nearly as good. And in fact, when you have a busy image like this one, Euclidean distance is going to tend to do well by having a uniform image that's the average intensity of this image, an average color, because that's going to minimize the squared difference. If you have another busy image, if it's exactly in phase, you'll get a small Euclidean distance. But if it's at all out of phase, you'll start getting very big pixel differences. So if you look on Euclidean distance, these very smooth images do pretty well. You never get those guys with using these binary codes. Now there's some obvious extensions to this. You could make the autoencoder work a lot better if instead of just feeding it images, you fed it images and captions represented as bags of words. And Nitish Srivastava has done that recently, and it does make it work better. Restricted Boltzmann machines make better models of bags of words than latent Dirichlet allocation topic models. And so you can use restricted Boltzmann machines on a bag of words at the front level for getting vectors to describe the bag of words. And you do the same thing for the pixels, and then you combine those in a deep autoencoder to get labels for the joint bag of words and pixels. And it's a win because it makes the labels of the images be more semantic because you're getting information from the words. It's a win because it makes the labels of the captions be more closely related, what you get from the captions be more closely related to what things look like. And the interaction during training just makes everything easier rather than more difficult. There's a less obvious extension that also works nicely, which is if you've got an incredibly fast retrieval technique, you can afford to do retrieval many times. And so Alex tried, instead of using the whole image for retrieval, in your database, take patches of images, so you get a much bigger database, but that doesn't matter. And then when you're given a test image, take patches from that, and then try retrieving patches. And say this image is similar to one of the images in the database if they have a patch that matches really well. And that'll cope with objects moving around and being in different positions in the two images. And that improves things significantly. There's many other transformations you could think of applying like that. You can only really afford to do that if you've got a technique that's incredibly fast, so you can do it many times. More recently, Alex has realized you can make the whole thing work much better. And here's what you do. His original image retrieval thing started with pixels and tried to get binary codes for pixels, and there was no knowledge of object classes at all. It was just pure unsupervised codes for images. But he's now developed a net that's very good at getting 1,000 different classes. So what happens if you look at the last hidden layer of that net? So the last hidden layer has 4,096 units in his ImageNet net. And what you can do is you can take the activity pattern in the last hidden layer produced by an image and ask, find me the other images that give me similar activity patterns in Euclidean distance. And so here's what they look like. This image here, according to Alex's net, is extremely similar to this image here. But notice the elephants are facing in different directions. The Euclidean distance in image space is huge here. But in terms of what's in the image, these are very similar images. So you would accept these as pretty good images that were similar to that one. It's even better for the aircraft carrier here. I assume that's what it is. I mean, it says this image is very similar to that image. And conceptually, they're very similar. They're both an aircraft carrier on some water with something in the background. But in terms of pixels, they're totally different. Or look at the sort of Halloween pumpkins. This image doesn't have a lot in common with that image, but it's the fourth closest image if you look at the last layer of the net. So Alex's proposal now is to take the representation of an image in the last layer and now apply an autoencoder to that and do all the semantic hashing, and he should be able to get a very nice retrieval technique. But that hasn't been done yet. The last thing I want to talk about in this lecture is another of the failures of backpropagation in the 1980s, when computers were too slow. It wasn't backpropagation that failed, it was those computer hardware guys just hadn't made decent machines yet. So backpropagation through time looked like it ought to be able to learn programs. You ought to be able to take a big net, run backpropagation through time, and have it learn lots of little programs that interact to predict, for example, what's going to happen next. And that would have been really nice. So people may have covered this already, but just in case, back-propagating through time is very similar to having a layered net and back-propagating through the layered net, except that the weights are tied. So this is a little recurrent neural net. This is the same net where I've blown up its states in time. So this is its states at time 0, this is its states at time 1, and so on. And this weight that says that the middle unit affects that unit one time step later shows up here, and here, and here. Okay, so it's just a layered net with tied weights. And we could think of it as you put inputs in here, you take outputs out here, and these are hidden units. And then if you gave me an initial state and said some final state you'd like, I could backpropagate and learn the weights. Or if you gave me a sequence of inputs and told me the sequence of outputs you'd like, as long as you don't want the outputs till two time steps later, then I could train up these weights. So given a sequence of inputs, they'll give the right sequence of outputs. And that's what we're going to try and do. Now the problem with those nets, as people may have mentioned, is that the gradients tend to blow up. So if you put in small weights and you backpropagate, by the time you backpropagated through many layers, you got very, very small gradients. If you put in big weights, by the time you've gone through many layers, you got very big gradients. And that made these nets hard to learn. One way of saying this, which seems sort of trivial, is if you take a number and you raise it to a large power, you either get something much too big or much too small, which is pretty obvious. Now, of course, you could try and keep the number be about 1.
It's worse than that. It's the fact that when you take a matrix and you multiply it by itself, you only get the largest eigenvalue, nothing else.
And that large eigenvalue is very big.
Right, but the point is, it's always the same. And so, if your matrix is degenerate, you get...
Yep. It's the power method for extracting a single eigenvalue. Exactly. Yes. Yeah. Okay, so they didn't work. But actually, if you initialize the weights carefully, you can make them work much better. And one thing that's happened in the last few years is that people developing things called echo state networks said, let's take networks like this, let's initialize the weights very carefully so that they neither blow up nor die as you run them. In other words, so you take the biggest eigenvalue of the weight matrix to be about 1.2, and then you put it through the logistic nonlinearity. 1.1 is not big enough, and 1.3 is too big. 1.2 is sort of ideal. And then the net will run for a very long time without either dying or blowing up. And then the people doing echo state networks said, okay, if we initialize like that, all we need to do is just learn output weights now. So you can think of them as freezing all W1 and W3 and W4, and just learning the W2, so that from these inputs and hidden stuff, they can predict the output. And that worked surprisingly well. Of course, it will work much better if you train these two. And as soon as you've initialized the net sensibly so it doesn't blow up or die, you can train recurrent networks. Before Ilya Sutskever realized that, he worked with James Martins, who developed a very fancy optimization method called a Hessian free method that was tailored for neural networks. And people in the optimization community developed Hessian free methods, but they'd never really tailored them properly for neural networks. And so what Hessian free methods do is they make very good use of curvature information. And what they're very good at is seeing a direction in the space where the weights are the horizontal dimensions and the badness of the net is the vertical direction. They find directions which have very small gradients, but even smaller curvatures. Because if a direction's got a very small gradient, you can still make a lot of progress by going a long way in that direction if it's got no curvature, if you keep going downhill. And the problem with training neural nets and everything else is that you have some directions with big gradients, but also big curvatures. And so you can make initial very fast progress, but you quickly go uphill again. You have other directions that may have very small curvatures, but they also have small gradients. And those are masked by these directions with big curvatures. And you need a very good method to be able to reveal, for example, the direction with the 100th biggest eigenvalue that happens to have very low curvature. The 100th biggest gradient, but has very low curvature. And James Martins got this working, and Ilya worked with him to make it work better. And they then wanted to apply it to recurrent neural nets. And we decided to try the problem of modeling language. Now, I have a theory of language. My theory of language is actually a tautology. It's definitely true. And it's like this. You have a mental state, a word comes in, and you have a new mental state. How could that not be true? And therefore, a word is something that operates on a mental state to produce a new mental state. And now we get the slippery little trick, which is, and what's more, your mental state is a vector and the word's a matrix and you operate on it linearly. That bit isn't so necessarily true. But we could try that. So the idea was, let's have 100,000 words, and let's have each of them be a matrix, and let's have a mental state that's a great big vector, and each of these words operates on your mental state to produce a new mental state. The problem is, your mental state needs to be a big vector, and this needs to be a big square matrix, and you need 100,000 of them, so you're going to need rather a lot of parameters. It would be much easier if, instead of modeling language at the word level, we modeled it at the character level, because there aren't many characters. We could take all the ASCII characters and strip them down to about 86 characters without losing much. Well, you have to be careful who you're talking to. I think we threw away all the French accents. But in Ontario, you're not losing much. And so then the problem is to predict the next character in a string, or to make a model that says you've got a belief state which is based on the characters you've seen so far. A new character comes in that changes your belief state. So there's good reasons for using characters. You're going to need many fewer parameters. Now, you're going to have to solve some difficult problems, like learning what words are. But compared with understanding natural language, that's a fairly trivial problem. So if you're hoping to understand natural language, learning what characters make a word ought to be trivial. Here's some other reasons for using characters rather than words. The web's composed of characters. You can just take stuff off the web and model it. It's non-trivial to find out which strings of characters are words, but it's trivial compared with learning all sorts of other things about language, like what it means. Pre-processing text on the web to get words is actually tricky. So it's not clear whether you want the words or the morphemes, and it's not even clear what the morphemes are. So for example, in English, most speakers of English don't realize that words starting, that SN is almost a morpheme. All words starting with SN, well, not all of them, but quite a few of them, have a particular aspect to their meaning. So SN words, on the whole, mean something to do with the upper lip or nose. There's just too many of them for that not to be true, like sneer and snarl and snot and sneeze and snog, and there's just a huge number. Can anybody think of an exception? Snail's an exception, okay, but they're kind of yucky. But snow, good, snow, thank you. So normally people shout out snow. So ask yourself, why is snow such a good name for cocaine? Okay. It's not just that cocaine's white, it's to do with the upper lip and nose. There's things like New York where it's not clear whether it's one word or two words. And there's lots of things like that in English. There's these little sub-regularities that you're not explicitly aware of, but at some level you know about. And then there's languages like Finnish. So this is Finnish, and it means, it's a single word, and it means despite his lack of understanding. So you can now start estimating how many words there are in Finnish, and it's going to be billions of words, right? They just stack these morphemes together to make up whatever it is they want. It's like German, but worse. Okay, so there's advantages to using characters. So here's a way to use characters without having nearly as many parameters as you might have thought. We're going to have a mental state that has 2,000 hidden units, and they're going to be logistic hidden units. And we're going to have 86 characters. And so you'd have thought each character had to be a 2,000 by 2,000 matrix. So that's 4 million right there. And so we're going to need about 1/3 of a billion parameters if you have 86 characters. But we can factorize things and do some sharing and use far fewer parameters. And the way we're going to do it is this. We're going to say, instead of going straight from here to here via a matrix multiply, what I'm going to do is I'm going to have things called factors. And I'll have about 2,000 of those. It could be more than 2,000 or less than 2,000. And the way each factor works is this. It applies a linear filter to this vector. So it multiplies the activities by some weights to get a scalar here. It applies a linear filter to this vector, but this is the 1 of n vector for characters, so in effect it just takes this weight. Then it multiplies these two scalars together and sends that product out here via these weights. And you have a whole bunch of factors that do that. So now that means characters can share things. For example, all the vowels could have strong weights to a subset of the factors that do sort of vowel-y things like predict that a consonant will come next. Another way of thinking about this is take the outer product of this weight vector and this weight vector to get a square matrix that has 4 million entries but only has 4,000 degrees of freedom. It's a rank 1 matrix. And each of these factors is a rank 1 matrix. And what a character does is put weights on a bunch of rank 1 matrices to synthesize a matrix with much higher ranks by adding together all these rank 1 matrices. And obviously if you've got a few thousand of them, you can synthesize more or less any matrix if you want that particular matrix. But this system can have far fewer parameters than having 86 arbitrary matrices and still capture the structure of what's going on. Okay, so the way the net works is this. It has some mental state. It sees a character. It uses its factors to get inputs for the next mental state. It takes the total input each of these units gets, puts it through the logistic function, and it gets some real valued vector there. There's nothing stochastic here. And then from that real valued vector, it's going to make a prediction via a softmax about what the next character will be. And now you're going to train it to maximize the log probability of getting the right answer. And so you backpropagate the cross-entropy error through here, through here, through here to learn this weight, and through here to learn these weights, and through here and down to the previous character, and through here, and you keep backpropagating it, and you backpropagate it for hundreds of time steps, or about 100 time steps. And so you can update all these weights. And the question is, can you see effects that are coming from many time steps ago? Like, for example, can it learn that after an opening bracket, if there hasn't been a closing bracket already, 30 time steps later, you're much more likely to have a closing bracket than the base rate for closing brackets, because you've got a bracket that's open. And indeed, it can learn things like that. And the only method we've been able to find that can learn things like that is this Hessian free optimizer. So let me show you some of the things it can do. Ilya took this net, initially used 5 million strings of 100 characters each, and started training after the 11th character. So he gave a kind of burn-in of 11 characters, and then the net started predicting, and he started backpropagating, and he ran for a month on a GPU board. His best model was not quite as good as the state-of-the-art, which uses lots of little neural nets and a manager that decides which one is making good predictions, and also updates its model based on words it's seen recently. Ilya's net is stationary in the sense that its prediction isn't learning at test time. You have to learn at test time to do really well at this. But it can do things like balance quotes and brackets over long ranges, and Markov models can't possibly do this, because a Markov model can't sort of ignore stuff and then say, it can't say, I've got an opening bracket, and there's all this stuff, but I'm waiting for a closing bracket, and please give me a closing bracket. If it wants to say that, what it has to do is take its whole state space and multiply it by whether or not by 2, one for having an opening bracket and one for not having an opening bracket. And every time it wants to remember one bit that it's going to carry along for a long time, it has to double the size of its state space. Whereas these neural nets can just set aside a few hidden units to remember that there's a bracket that's open. So potentially they're much more powerful if you could train them. And this is an example of them doing that. So after it's trained, it's fun to get it to now generate text. So one way to get it to generate text is to give it an initial string and to ask what character you think is most likely to come next. Then you produce that character, you tell the net, okay, that's what did come next, now what do you predict for the next character? Well, if you do that, it quickly starts saying the United States of the United States of the United States of the United States of the United States. That's the sort of degenerate loop in Wikipedia, in English Wikipedia. It's much better, obviously, to take the distribution it predicts and sample from that distribution. So if it says there's a 1 in 1,000 chance that the next character is a Q, produce a Q 1 time in 1,000. Now, obviously, if you do that, you'll sometimes be producing characters the net thought were very unlikely, and so it'll sometimes do weird things, which it knew were weird, it thought they were unlikely. But what's amazing is that most of the time it does something very reasonable. So I'm going to show you some text generated from the net. We generated a lot of text from the net, and this is selected to be a particularly good passage. So there's cheating going on because we've selected a passage, but there's not much cheating because it's a contiguous passage, right? If we were producing garbage, we couldn't have found a long passage that was good. So the net generated this. There was some stuff came before this, and this tells you a lot about what the net understands. For example, it really understands what a word is. There aren't any non-words here. There's initials and stuff, well, not in this one, but in a later one. Yeah, initials. It understands what initials look like too. It has a limited it either has a limited grasp of geography and intelligence agencies, or it has a great sense of humor. It doesn't stay on topic, right? It stays on topic within a sentence, but then it switches to something else. A good thing about this is you can take this text and you can search Wikipedia, and if a string is not in Wikipedia, it cannot possibly have been in the training set for this net. Okay? So you know, for example, that you can look for escape during an alliance, and it probably isn't there. Most of the strings of 4 words here are not in the Wikipedia. It's really generating this stuff. And it generates sort of technical terms like proton reticulum, but it stays on topic for a whole sentence. And it sort of clearly has a very shallow kind of semantic understanding. So, such that it is the blurring of appearing on any well-paid type of box printer. Well, you've got blurring and appearing and box printer, which are all to do with kind of the appearance of stuff and the production of text. So it gives the impression that it understands quite a lot. And the problem with this thing is exactly the same as the problem with grading midterm tests. Did they really understand what I said, or have they just managed to generate strings of words that look quite plausible? Here's some more text. You can see, look, you wouldn't say he forgave Opus Paul at Rome, but you know these things are very highly associated, right? There's Opus Dei, and there's a pope called Paul, and there's Rome, and there's all that stuff. It does produce non-words. Here's a non-word. But you're not quite sure that's a non-word, right? It's a pretty good non-word. It produced another passage, it produced a word continged, right? Well, continged is probably a non-word, but sort of continged on not knowing what's going on, it could be a word. It does very well with initials. And notice here, opening quote, bunch of words, closing quote. Markov models can't do that. Okay.
In the 4th line, I mean, between the 3rd and 4th line, it says Arab women's icons in, and there's nothing after the in.
Right, remember I said at the beginning, there's sometimes when it's, of all the things you've seen, there have to be some characters that it thought the chance was less than 1 in 1,000, because you see more than 1,000 characters, roughly speaking. That's probably one of those places. It thought that the next character, you know. Also, because it's trained on limited strings, it can sort of get discontinuities. But it's doing pretty well. It's doing much better than we expected.
It looks like it has 2 spaces after the end.
Yes, it might well have 2 spaces there. So I did actually some tests on it. So if you give it Sheila and then a nonsense word, thrunge, most English speakers will say that thrunge is probably a verb, and most English speakers will say either thrunged or thrunges is the most likely completion here. And it thinks both of those are pretty frequent, and thrunges is the one it likes most. So I then thought I'd fool it and put a comma after Sheila and put a capital with thrunge, so it looked like a list of names. And I expected it to say Sheila, Thrunge, Fred. It didn't say that. It knows a lot about proper names. And it made up the name of this guy, Thrungelini Del Rey. Thrungelini Del Rey, I've decided, is actually a maker of exotic movies who has a Spanish father and a Swiss and is an Italian mother and is currently living in Switzerland. Okay. You can give it the meaning of life is, and you often get nonsense, but occasionally you get interesting things. In fact, quite often. So in the first 10 tries, this was the 6th try. If you got 42, it wouldn't be interesting, because that's in Wikipedia, I bet. But you can find that somewhere. This is not in Wikipedia. I went and checked. It doesn't say the meaning of life is literary recognition. It would have been better if it said the meaning of life is getting lots of citations, but this is close. Ilya then trained it a lot more. Oh, before I say, yeah. So here's some of the things it knows. It knows lots about words. It knows what words are. It knows lots about numbers, proper names, dates. It knows that you often start paragraphs with, in 1973, things like that. It can count brackets. If you give it one opening bracket, it will produce a closing bracket, typically about 5 to 10 characters later. If you give it 2 opening brackets, it'll produce a closing bracket only a few characters later. It gets very anxious with 2 opening brackets. It's thinking, I got too many brackets open here, but it can't tell the difference between 2 and 3. It counts none, 1, or 2. None, 1, or many, basically. But it definitely behaves differently after 2 opening brackets than after 1 opening bracket. It knows a bunch of math, too. For example, if you say F opening bracket, it will almost certainly put X closing bracket. It knows an awful lot of syntax. It wasn't just, but it's sort of short-range syntax. And of course, it's not in the form of proper syntactic rules like a linguist would like. It knows lots of semantics, but it's shallow semantics. I only ever saw it say Wittgenstein once, and it said it about 10 words after Plato. And I'm convinced it sort of knows that Wittgenstein and Plato have something to do with each other. It knows that cabbages and vegetables tend to occur in the same sentence and things like that. Its kind of semantic knowledge is like the knowledge that I can make you exhibit if I force you to answer questions very quickly. So, for example, I need a cooperative audience here of people who haven't seen this before. I'm going to ask you a question, and you have to shout out the answer that comes into your head. And no, I haven't asked the question yet. And the first person to shout wins the prize. And the essence here is speed. Don't filter it to say, that doesn't make sense. Just shout the answer as fast as you can. Okay, what do cows drink? Milk. Very good. Now, it's true some cows do drink milk, but cows drink water. But cows and drink are associated with milk, right? And that's the kind of knowledge this net has. It has lots of that knowledge. So Ilya then trained it some more. And philosophically, I believe that if you get a long enough string of text, there's enough information in that string of text to understand the world. Now, you have to be very careful philosophically. To build a model of the world, that model's still up for interpretation, but the model ought to be able to, for example, answer questions. Sort of what it all really means. This is like the Matrix movies. What it all really means is another question. But with enough text, you ought to be able to understand English so that you can answer questions. And so wouldn't it be nice if you can take this neural net, you can train it up on 1 billion characters in Wikipedia, then you can ask it the meaning of life and it can get the right answer. So this is the closest we've got so far. And this was one of its first 10 attempts after we'd given it a lot more training. Because of the way PowerPoint works, I cannot show you this in PowerPoint. But I can show you it like this. So what we're going to do now is get it to predict 1 character at a time. It's more fun like this. You run till you hit a full stop. His syntax isn't perfect. And honestly, the net did this, it wasn't me. Okay. It's got close. That's the end of this lecture.